And we are live. Hi, I'm Frank.
Hi, I'm Jackie.
And we're here for the AST111x first Google Hangout. Let's see. So I guess the plan we're going to go with today is Jackie's going to lead off with a little bit about constellations and star charts. And then I'll do a little bit about time, and then we'll take some of the questions that were suggested in the discussion forum for the course.
Okay, so starting out with constellations, Frank, is my image kind of freezing sometimes because it seems to sort of stall on occasion?
Not for me.
Okay, good. All right, so I'm going to give you some advice on how to do your night sky observing using proper resources. And I'm going to give a quick tour of the constellations that are in the Northern Hemisphere, and then a quick tour of how to find the Southern Celestial Pole, because there is no South Star and there is a North Star. So it's harder to find South in the Southern Hemisphere. So I'm going to give a quick tour of that as well. But let's start with some resources. In the in-person labs at Arizona State University, when we actually got on the roof and used the telescopes, the students typically are required to purchase an Audubon guide. And I've lost the dust cover, but this is the Audubon field guide to the night sky. It's really, really great. There are special books that you can use for the Southern Hemisphere. This one is somewhat Northern Hemisphere tilted, but it's still got a really good general purpose bunch of material for both hemispheres. And it comes with, there's a blue section, which is full of every single constellation. And it includes skies, pictures of the night sky for different months and at different latitudes. And then it has pretty pictures of deep sky objects, so nebulae. And then it has all this information about all of these things. So it's a really, really great just overall guide for the night sky. And if you're in the Southern Hemisphere, I do recommend picking up a Southern Hemisphere tilted book. And we can start a thread where I make some recommendations for those, because the one that I have is out of print. But I also recommend everyone pick up a star wheel. And again, they make these in Northern Hemisphere and Southern Hemisphere flavors. So this is a Northern Hemisphere one, as evidenced by the fact it says north at the top. And in fact, they often come with very specific latitude markers. So this one actually says 30 to 40 degrees north latitude. And if in lower down in Mexico or something, I strongly recommend picking up 10 to 20 or 20 to 30 degrees latitude so that you actually get the right constellations. How to use them. So we actually have to, some people figure this out on their own and they're happy, but sometimes it takes a little bit. So there's two wheels on your star wheel. There's an inside wheel, which is the time of day. So there's a time of day that says midnight or 8 p.m. So you line up your time of day with your time of year. And the year is the outside wheel. In this case, it's blue. And so you're going to find June. I want to look at the sky at midnight at the middle of June. I want to line up midnight, middle of June. And this is what my sky looks like. And what am I looking at here? The whole thing turns around your celestial pole, the relevant celestial pole. So the pin in the middle is where Polaris is. And the horizon is the hole, like the whole thing that you can see is edged by the horizon. And north and south run right through the middle. So this is the line from north to south is known as the meridian. Objects are highest in the sky when they transit the meridian, when they cross the meridian. And this is the thing. Oh, another thing about reading star maps is they're not meant to be read like normal maps. You'll notice when you hold them, any star map, the east and west are backwards, which drives people bananas. But it's because you're meant to hold them overhead. And when you hold them overhead, voila, instantly east and west will actually line up with true east and true west, and then you should be good to go. And so that's it for using maps and Star Wheels. I'm now going to do a screen share and give you guys a quick tour of what's actually up in the sky right now. This is Frank, let me know if this is working. Screen share, desktop. All right, are we good? I think so. Okay.
I see it.
So first of all, let's start with planets, because that's something everyone should have in common, unless you're actually standing at the North Pole. So right now in June, if you go out in the evening after the sun has set, you should see Jupiter moving into the west, and it's going to be kind of trending towards the west or even the northwest. And if you are very far north where the sun sets very late, you could actually see Jupiter setting rather than up in the sky. It depends on what time of day the sun actually goes down where you are. But Jupiter is up in the west, should be towards the south. Planets are going to be lined up in a line towards the south if you're in the northern hemisphere. If you're in the southern hemisphere, then this is not correct. You're going to be looking north. And everything will be flipped. But it's basically the same planets. You'll have Jupiter setting in the west, and then you'll have Mars is actually distinctly orangey, yellowy, reddy. I know that's kind of wishy-washy, but some people, it really depends on your color vision. Mars looks very orange to me right now. It's actually at its closest point to the Earth. It's at what's called opposition, and it's quite bright, and it's quite orange, and it's actually rising right when the sun goes down right now for me. The Saturn, the other planet that's up in the evening is Saturn, and then Antares. And Antares' name means not Mars. So normally it's easy to confuse Antares and Mars because Antares is also pretty clearly reddish. And the difference between stars and planets is a general rule of thumb is that stars twinkle and planets don't. So Spike is here in between Mars and Jupiter. It's not going to twinkle. But right now, Mars and Jupiter are just so bright that you're really not going to have any confusion between them and Spike and Antares because they're just the brightest thing in the sky right now. Saturn's less bright. So you might actually need to use the stars twinkle, planets don't rule for that. Moving on to the northern hemisphere. If you look north in the northern hemisphere, typically people are trying to find the North Star. And the easiest way to find the North Star, particularly if you're at a sort of washed out site like I am, I'm in downtown Phoenix, and the situation in downtown Phoenix is there's a bright sky, but it's not as horribly bright as it was in downtown Cleveland, or certainly as bright as it would be in Beijing or New York City. So I actually can see the Big Dipper. And that might not actually be the case in really big cities and the centers of them. So I can see the Big Dipper and I can see Cassiopeia. And generally the rule of thumb is if the Big Dipper is up, Cassiopeia is not. They are circumpolar. So for most latitudes in the northern hemisphere, these things won't set. They rise in the east and they try to set in the west. But then they end up just sort of skimming around the northern horizon underneath the Little Dipper. So technically, you can always see the Big Dipper and Cassiopeia, but depending on how much fuzz you have, how much haze you have down at the bottom of the sky, you might only be able to see the one that's highest in the sky. So you use the Big Dipper, you use these two stars at the end of the bowl of the Dipper to find the North Star. And for me in Tempe, I can basically just barely see the North Star. And I can see these two bright stars at the edge of the Little Dipper, and I can't see any of the stars in between. Going out to a darker site in the suburbs or out in the countryside, the constellation pops right out. There's also another trick you can do with the Big Dipper, and it's called arcing to Arcturus. So Arcturus is kind of this bright star. It's a giant star. It's kind of near as stars go, and it's also got I think it's got a little bit of a yellowish tint to it. And it's often in the middle of the sky doing kind of like nothing off on its own. And it's hard to tell which constellation it belongs to. And you know it's Arcturus because it connects to the Big Dipper like this. So you take the handle of the Big Dipper and you arc to Arcturus. You can actually draw that out certain times of the year, and you can arc to Arcturus Here we've flipped the whole sky. So now we're kind of looking overhead. So now Polaris is this way. We can arc to Arcturus, and then we can spike to Spica. So those are the lines. Oh, and then there's a line to Leo. If we go back the other way through the Big Dipper, there's a line to Leo. You see how they do this with the AASSLL. So those are the basic mnemonics for the northern sky. I actually think that Leo and Virgo are kind of setting when the sun comes up, or when the sun goes down. When the sun goes down and it gets dark enough to see things, right now I think Leo and Virgo are setting because they're spring constellations. And so even in the southern hemisphere, that's going to be true, that Leo and Virgo will be setting for you because they're autumn constellations for you guys. Moving on to the southern hemisphere, where things get fun. So there is no pole star. So here's a really pretty picture of, not picture, but, oops, how to find stars using astronomy charts. Here's a really nice little image diagram of what the southern sky looks like. And they've circled a dot here saying it's a pole star, but for 900 locations out of 1,000, you're not going to see anything really clear there. And the way most people find the pole stars, they find the Southern Cross, which is bright, and you won't be able to miss it. And there's two ways of doing it. The first is you sort of take the length of the Southern Cross long ways, and you jump 4 times. And that gives you the South Pole Star. There's another way of doing it, which is to use these 2 pointer stars. And this is in the Centaurus constellation. And the pointer stars, and they're again going to be really clear. I think it's Alpha Centauri and Rigel Kent. And you can draw a line between them and make this little T. And so the line of intersection between the line through the Southern Cross and this line gives you the Southern Pole. And again, the Southern Pole is the point in the sky where everything twirls around it over the course of the night. Actual due south is the closest point on the horizon to that. I'd just like to draw your attention to these 2 little blobs in the southern sky, say SMC and the LMC. These are the Southern Magellanic Cloud and the Small Magellanic Cloud and the Large Magellanic Cloud. And they really do look like clouds, even if you're at a very dark site. You actually won't see them unless you're at a dark site. I spent 6 months in Australia, and for the first 5 months, I was convinced they didn't exist because I just never been at a dark enough site to see them. But they look like clouds. They really do. And they are actually satellite galaxies of the Milky Way. They are orbiting the Milky Way, and they are currently actually interacting with one another gravitationally and being harassed, I guess is the word. We actually use this term in galaxy mechanics. They are being tidally harassed by the Milky Way itself and pulled apart a little bit. And then Canopus is this other bright star, which is the second brightest star in the sky, after Sirius. And people in the northern hemisphere don't get to see Canopus at all. The sky in the southern hemisphere is somewhat better because you have a better view of the Milky Way's bulge and all the bright stars that are associated with it. And I guess that concludes our tour of the night sky. If you have any questions, please ask them in the discussion board, and I'll try to answer them as quickly as possible. Frank, back to you.
Okay. So you're off on screen share?
I'm working on it.
Okay.
So, what's our next topic?
Next topic, I'm going to do a little something on time, and then we'll go and do some of the questions that are posed on the discussion thread. Okay, so let's see. I'm going to do a screen share. Let's see. What's my screen share? Screen share my desktop. Let me know if this shows up okay. Just thinking about it. All right.
Yeah, it's good.
We good?
That's it. Yep.
Okay. So I want to talk a little bit about time, and the passions of astronomy are no less profound because they are not noisy. And that's a quote out of a John Steinbeck novel called The Short Reign of Pippin IV. Pippin was an amateur astronomer who became king of France because he had some lineage to King Charlemagne. And he was put up in the position basically to be overthrown. So this was the only political satire that John Steinbeck wrote. And so the cover image there, Pippin found that he didn't really like the life of a king, too invasive on his privacy, and certainly could not use his telescope. So he would often dress up as a commoner, get on his motor scooter, and take off to go continue his amateur astronomy. Eventually, he was overthrown, and he got to return to his life as an astronomer. So time through the ages is what we're going to talk about. This is an appropriate little piece of artwork because it's going to be about clocks and their relationship to the celestial sphere, objects on the celestial sphere, whether that be the planets, particularly the moon, or the stars. So 'tis the season. So when we start off, right, agricultural dependence means knowing when it's time to plant, when it's time to plant your crops, when it's time to pick your crops, when the first frost is going to come, when you need to till the land, and so on. So as long as you're keeping time by what the sun says, all is great. But as societies grow more complex, they typically want fixed dates for things like your birthday, or when to pay your taxes, when to have certain festivals of freedom, or whatever it may be. And so this immediately introduces the difficulty of keeping the seasonal clocks, the time that the sun says, versus the calendar clocks, which is the time that man sets, synchronized. And how you keep those two synchronized has been an ongoing adventure for the past several thousand years. There's just a nice image there of the 4th of July, an example of a fixed date in Tempe, Arizona in 2007, and some of the fireworks going off. So we've got this tension between seasonal clocks and the calendar clocks. So what's a year? For reference, as we go along, the seasonal year, what the sun says, is defined as vernal equinox to vernal equinox, so spring equinox to spring equinox. And it's about 365 days, 5 hours, 48 minutes, 6 seconds, or about 365.2422 days. And of course, this is a famous art piece on the persistence of memory and the melting clocks from Salvador Dali. So the yearly calendars were often based on a summer solstice to summer solstice, or when a particular star happens to first rise with the sun, and that is called the heliacal rising. The image here is showing the heliacal rising of the star Sirius. So the horizontal line going across is the horizon line, so everything below the line would be covered by the Earth. Everything above the horizon line would be sky. You can see the sun is just about to break the horizon for sunrise. And then there's the star Sirius in Canis Major, which is leading the sun a little bit. And so in this particular case, this is taken in Alexandria, Egypt in the year 2000 BC. And so you can see that Sirius is just rising with the sun. And so the Egyptians used Sirius, which because it's the brightest star in the sky, and it rose in July when the Nile was in flood. And because the Egyptian economy was based on the Nile, the heliacal rising of Sirius was the most important day of the year, and thus the first day of the year. So if you like, their January 1st, their start of the year, was actually in July when Sirius rose with the sun, the Nile was in flood, and it was time to get going. So Sirius, here's a rendition from Uranographia from Johann, is the brightest star in the constellation Canis Major, and it is sometimes known then as the dog star because the Canis is the dog there. And it's from the Egyptians' use of the heliacal rising of Sirius in early July that is where we get the English phrase, the dog days of summer. And so that phrase is actually quite old, and it's still with us on the dog days of summer and the rising of Sirius. And I clicked the wrong button.
It's weird because Sirius is normally a star that's associated with the winter, because that's when you actually go out during prime time night viewing and see it. It's part of a winter constellation, but it's behind the sun in the summer, so you get your heliacal rising in the summer.
Thank you. That's correct. So now that we've got a year, whether you mark it as summer solstice to summer solstice, or you mark Sirius rising, that's kind of long, and so people wanted to break that down into components, a little bit shorter periods of time. And so how to mark time intervals within the year. And the first marker used was the moon, and this is the root word of month. Okay, so month comes from moon. And there are two main obstacles with using the moon to subdivide the year. The image here is the Aztec calendar stone, which is the how they marked off time, which was a lunar-based calendar. So two problems with using the moon to subdivide the year. The first obstacle is that the lunar month varies between about 29 and 30 days. It's not constant. And the reason it's not constant is because there are actually two periods going on. One is called the synodic period. This is the time between identical sun, earth, and object alignments. So for example, full moon to full moon. Okay, so this is easily observable, but it's not too useful. Okay, it's kind of an apparent looking thing. The one of interest is the sidereal period, which is another piece of jargon. And this is the time between identical star, earth, and object alignments. This is the real period. And so if you take sidereal and you just chop off the first part of that word, side, and just go real period, this is the real period. This is the one that you use in physics formulas. This is the one that you would put in Kepler's third law, for example. But it's also harder to observe. Or you have to be aware of the observation. So let's do a little walkthrough on a hand-clicked animation, if you like, on the difference between the two. So let's start off where we have the sun. We have the earth going around the sun. In this rendition, we have the moon going around the earth, and then we have a distant star. And in this time equals 0 shot, we've conveniently lined everybody up along the black line there. So the sun, the moon, and the star are all lined up. Now we're going to let time go forward. Whoops, wrong way again. We're going to let time go forward in this. And so the earth goes around the sun, the moon goes around. And when you have the same earth, moon, star alignment, this is the real period. This is the period that you would put in Kepler's third law. The real period of the moon is 27.322 days, and that's a lot of decimal points, a lot of precision on that number. But the moon is not a full moon. Okay, it's almost there, but not quite. Gosh dang it. So you have to wait a little bit until the moon travels that extra little bit of distance around the Earth. Why? Because the Earth has moved along in its orbit to get to the full moon. And it's this time to reach the full moon alignment again that is variable, 29 to 30 days, in large part because the Earth does not have a perfectly circular orbit around the sun. So there's a little bit of difference there between the real period and the observable, the full moon to full moon period, if you like. The other obstacle with using the moon to mark time within a year is that the year can't be evenly divided by sort of an average full moon to full moon time of about 29.5 days. So 12 lunar months is about 11 days too short, 13 lunar months is about 19 days too long. And so if you use such a calendar to mark time within the year, the calendar will slowly but surely get out of step with the seasons. And if you wait long enough and you don't do anything, then you will find that eventually the hottest time of the year will occur in what you would be calling the winter months. And so that is the essence of this synchronization between the seasonal clocks and the clocks that man is going to impose in order to keep sort of a uniform time. So many cultures got around this conflict of not being easily divisible by inserting an extra 13th month every few years so that the seasonal and calendar years would stay synchronized. So a little side here. So it was accepted practice in Babylon for about a month after a wedding that the bride's father would supply his son-in-law with all the mead he could drink. So mead is a honey beer, and since their calendar was lunar-based, this is where we get the word honeymoon as a shortening contraction of the two words honey month. And so the honeymoon part of a marriage goes way back to the Babylonians. And you can imagine getting like free beer for a month after you got married. That's wild. Maybe they didn't have a lot of beer then, I guess.
I don't know. I can drink a lot.
Honey beer. You can even get it in Oregon right now, right? Portland Brewing Company will sell you some honey brew. But the moon and the lunar calendar is we have all kinds of terms that come from that. The word lunatic, from lunatic, where we get the words blue moon, wet moon, harvest moon. There's all kinds of terms that we use associated with the moon. So the Egyptians decided that the moon, trying to mark time with the moon, was a little too nutty. And so they took a more radical approach. They divided the year into 12 months. This is where we get it from, of 30 days each for a total of 360 days. And you will note that there are 360 degrees in a circle. That's where it comes from, right? Why weren't there 17 degrees in a circle or 4,220? There's 360 degrees in a circle because there's roughly 360 days in a seasonal year. But they knew that it was not exactly 360. So at the end of every year, they added 5 days for an approximation of 365 days. But even the Egyptians recognized that this was not perfect, that over time there would become a synchronization problem between the seasonal calendar and the imposed calendar. And so extra days were randomly inserted to keep the two synchronized as they went along. So the Romans came, and the Romans, when they rose to power initially, had a surprisingly messy calendar. The year was 10 months long, and March being the first month of the year, and extra days were inserted at random to keep the seasonal and calendar years together, right? This is a recurring theme now, right? We've heard it several times, right? You got to keep doing this stuff to keep the time that the sun says versus the time that your calendar is saying. But it is from that Roman calendar of 10 months long, this is where we get the names of our months: September, October, November, December, for being the 7th, 8th, 9th, and 10th months in the Roman calendar. And if you speak any sort of a language related to Spanish, for example, You can count off 7, 8, 9, 10 in Spanish, for example, and they will sound like September, October, November, December. So of course, they're not our 7th, 8th, 9th, and 10th months anymore, right? We move them to the end to have 12, but that's the root of those month names. So that was still crazy. And so 1 year before his death, it was Julius Caesar who instituted a new calendar with having 12 almost equal months. March is still going to be the first month of the year. That's where they have their January 1st is the opening of March. And the total in that almost equal months was 365 days. Okay, so far he hasn't done anything. He just rearranged things a little bit, so no big deal there. But then he adds an innovation. He adds something new to it. What he says is that every 4th year or leap year, 1 extra day was going to be added at the end of the year. So that would be their December. And so this gave an average year of 365.25 days, okay, which is a little bit better. You didn't have to insert days at random. It was very scripted now. So Julius liked his new calendar so much that he decided to take the name of a month for himself. And this is where we get the name June for our calendar month, from Julius Caesar. July. My bad. So he took July for Julius Caesar. Power loves money and money loves power. And in Julius's time, the primary wealthy people at the time were the Juno family. And Julius decided to honor his benefactors by giving them the name of a month as well. And this is where we get the name June from the Juno family. So June and July, Juno family and Julius Caesar are where those come from. And of course, now the pattern is kind of set. And so every emperor that comes beyond Julius is so great that they have to rename a month for themselves too. Fortunately, the only one that stuck was Julius's grandson, Augustus Caesar, who took August. And so this is where we get the name of the month, August. So our summer months, June, July, and August, are all due to the Roman elite. Okay. So the Julian calendar, as it was called, and it was widely adopted, was pretty good. 365.25 is pretty good, but it's about 11 minutes too long over the courses of a year. Or if you wait 130 years, it will be out of sync by a day. And if you wait 1,000 years, then it's going to be out of sync by a week. But who's going to worry about that? Let's just let it roll. Well, guess what? 1,000 years did roll by. And so by 1582, the seasonal and calendar years were about 10 days out of sync. And this was beginning to be a problem. And so it was Pope Gregory who's going to make some adjustments to the Julian calendar, and he introduces what is called the Gregorian calendar. I want you to take a close look at this calendar, October 1582. And what do you notice about that? Well, let's see. We have October 1, 2, 3, 4, 15. So his first move is to synchronize the seasonal calendars and the human calendar by chopping 10 days right out of it. This started panic near riots. Do I lose a paycheck? Do I have to pay taxes on that day? What if my birthday was October 5th? I just lost my birthday. And so there was all kinds of kind of social unrest from just, do I have to pay taxes on those 10 days? Those kind of questions. So quite a bit of little social unrest from chopping 10 days out of the calendar. But he resynchronizes the seasonal and calendar years. He is the one where we get January 1st marking the beginning of the year because we can't have that pagan Roman March to start the year, so he shifts it to January. And he keeps Julius's great innovation of every 4 years we're going to add an extra day, but rather than adding it at the end of the year, he shifts it to being added in February. And so far he hasn't really done anything. Okay, he's resynchronized the calendars, he shifted the origin from March to January, and he shifted when you're going to add the extra days. But no great accuracy, no additional accuracy is added at this point. But then he institutes another correction, where he says that century years that are divisible by 400 are also leap years. So 1700, 1800, 1900 are not evenly divisible by 400, so they are not leap years. But 16,000 and 2000 are evenly divisible by 400, and so they also become leap years. So this is a correction, and so this Gregorian system is now only 38 seconds too short of the true seasonal year, or about 1 day in 2200 years. Okay. So what are we going to do? Are we going to wait 2200 years before we have to do another calendar shift? No, we don't do that anymore. We're done with that game. And we have the technology where we can detect fractions of a second difference between the seasonal clock and the calendar clock. And so currently 1 second is added to the calendar clock at midnight on 2 specific days, June 30th or December 31st, whenever the difference between the seasonal year and the calendar year reaches 1 second. Okay. So the calendar clock is maintained by an organization in France using a worldwide network of atomic clocks. And the seasonal clock is based on observations of Earth's rotation by the International Earth Rotation Service. One of those is the U.S. Naval Observatories shown in the shot here. And so these rather bunker-like looking buildings with bars on the window and everything are measuring the Earth's rotation with fantastic accuracy. So if you wonder why they have bars on the window, like somebody's going to get in there and change the Earth's rotation or something. So why are there 7 days in the week? We covered this in course. Our 7 days of the week actually come from the Norse Celtics. So each day of the week is named for an object that moved on the celestial sphere that was rare enough that you had to honor it with something. And so we have Sunday, Moon Day, Tuesday, Moon Day, Thor Day, Freya Day, and Saturday. So we covered that a little bit in class. But let me ask another question. Where did time zones come from? Who invented that? Why? When? Why do we have time zones? So the essential reason why we have time zones is because of transportation. So before time zones were instituted, every locale set their clocks according to what the sun was at that time. So for example, if you were living in Phoenix, you would have one clock set, and if you were living in Yuma, Arizona, you would have a different clock because Yuma's in a different location than Phoenix is. And so there would be a difference in the time there. That would be your local astronomical conditions, your local zenith. But this created major confusion, particularly when trains started to dominate the transportation scene. It wasn't clear when you were departing and arriving at different locations, whose clock were you referring to? And it was a continuous, right? Because it's a continuous local condition. And so that just was just chaos. And so time zones were actually introduced by the railroads in the United States in 1883 in order to standardize the schedules. And then it was in 1918 when Congress took this convenience that the train industry had dreamt up and made it official for all of the US. So all time points were to be time zoned. And then later, about 10, 20, 30 years later, when the equivalent of the United Nations at the time instituted time zones across the globe. And as you can see from this picture, they are hardly straight lines, mostly, because there's lots of allowances for geopolitical changes in the boundaries to those time zones. And that's all good. And then, of course, at some point, you've got to have a place where the day actually changes. And so that's somewhat put out in the middle of the Pacific Ocean there. That's the dark line over to the right, where you have the international date line, which is where it shifts from one day to the next. Okay, so that's a little bit about time. And we'll move on and start taking some of the questions from the Google chat. All right, let me get out of here. How do I?
Okay, so I think Frank is going to take the precession and or tilted Earth question in a second. But to give him a break, I'm going to talk a little bit about some of the other questions. First, we have a question about the science behind Project Apollo. Specifically, how did the voyage from the Earth and the Moon, distances, trajectory, etc. apply? So because time is running short, what I'm going to tell you is, first of all, Project Apollo, which is the moon missions. Those were the original missions to the moon in the 1960s. The very first voyages by the United States National Aeronautics and Space Association. So NASA's first missions to the moons. And I think the first moon landing happened in 1969, and that's when Neil Armstrong and Buzz Aldrin landed on the moon. And if you really want the history of that, which is amazing and wonderful and fun, I strongly recommend a series of video It's like a documentary dramatization called From the Earth to the Moon. From the Earth to the Moon with Tom Hanks. And Tom Hanks is also the actor who played Lovell in the astronaut Lovell in the Apollo 13 movie. So Apollo 13 was the Apollo mission that didn't make it to the moon because they had a problem. This is where Houston, we have a problem comes from. And so there's a lot more, it's a lot more about technology than it is about science. Science, in terms of planetary science, didn't really enter the moon missions. They were really about politics and beating the Russians to the moon, because everyone was convinced that whoever owned the skies would basically win the Cold War. And also they were afraid that the Russians would be doing nuclear testing on the far side of the moon where nobody could see them doing it, and violating the nuclear test ban treaty that way. But fundamentally, the motivations behind Project Apollo were political. And there's right now, I mean, the amount of the United States gross domestic product that went into making it happen in the 1960s is crazy. And it was over the top. This is the kind of money that NASA can only dream of today. Really, it's a colossal amount of money, and we did it. And then it continued to be expensive. And once we had established our presence on the moon, we decided it was too expensive, and we stopped doing it. The last mission to fly was Apollo 17. The first mission to actually land on the moon was 11, and it actually took us. There were several stages to get there. There was the Mercury missions. Before that, I've lost one of the mission categories in between that, but we had to learn how to go into orbit. We had to learn how to put a man in orbit and bring him back down safely. The Russians practiced with dogs, and the Americans practiced with monkeys. And the first dog, what? Are you going to tell the Laika story?
No, Gemini mission.
Oh, Gemini, thank you. Mercury, Gemini, Apollo.
Right.
And a lot of the same names come up in Mercury, Gemini, and Apollo. They had the same cast of Air Force pilot level, like all of these astronauts at the time. They're all white guys, and they all have really strong chins because they were Air Force pilots. And they the only exception to that is Jack Schmitt. In Apollo 17, we actually sent a real scientist, a geologist. We finally sent a geologist to the moon. But they actually had to train the Air Force pilots in geology so that they could look at the moon and say, report back what they were looking at. So they did these awesome field trips to Arizona to like learn about rocks so that they could talk back to the geologists in Houston about what they were saying. So it's a really fun process, just like how you build a moon lander, how you build a moon suit. And then there's like an entire hour about like what it was like for the wives, because they all lived together in this little community. And it was very stressful for them because some of them lost their husbands. Because not every time you get on a rocket, it works. Sometimes the rocket catches fire. Sometimes the rocket blows up. And so there were a lot of very stressful times for everyone, very exciting, very stressful. So it's a really great little documentary called From the Earth to the Moon. But the science involved is mostly physics. And it really did, they had to do it stepwise to be able to develop the skills and the technology to do it. Their computers were basically not that much stronger than the calculators that you can buy in the grocery store. But they took up the size of this room that I'm sitting in right now because they were made with vacuum tubes instead of with silicon chips. And there were all these support staff down in Houston and in Florida. Women were used as computers. So it used to be that women did all the computer programming. And they were called computers because they sat there with slide rules doing the calculations. And so women, there's a group of white women and a group of black women who were actually sitting there doing the calculations in Florida to launch rockets. And what's really scary about rockets is when you're in orbit, there's a thing where they have to match the incoming spaceship with the spaceship that's in orbit. So the spaceship that comes up from the moon, the lander, comes up from the moon, and it has to join with the orbiter that's in orbit around the moon. It has Michael Collins. So this is why they had Air Force pilots. So Neil Armstrong and Buzz Aldrin had to join their moon lander to the orbiter with Michael Collins to get back to the Earth. And this was a whole skill set that they had to practice on in orbit around the Earth, because it's like the analogy I've heard is trying to throw a football over a house, an American style football that you actually throw instead of kick. Trying to throw a football or a baseball over your house while your friend is standing on the other side of the house throwing another baseball going the other way, and you have to hit in the middle. So the two baseballs have to hit each other. And that's the analogy for how hard it is to actually join two spacecrafts together over the moon. Because they're also moving like 10,000 kilometers an hour when they actually are coming in towards each other. So you also slow down and decelerate. It's a very, very tricky thing to do. And I think that's all I have to say about that. Frank, do you want to take the next question?
Yeah. Tom Wolfe's The Right Stuff. Interesting read. Okay, let's see. I will take, I guess, the first one here. 2 questions. How did the Earth get its 23.5 degree tilt? This will be somewhat a topic that we will cover in week 4. So right now we're covering planetary motions and gravity. In week 3, we cover light, we cover telescopes. And then in week 4 is when we start planets proper. And one of the first topics in there is the formation of the solar system. And as we will see when we get there, there is a period of great violence. There weren't always just 9 planets. At times there was hundreds of planetesimals, as we call them. And those planetesimals bang into one another. It's like a pachinko machine going off. It's a rough and rumble time. And so this is what is believed to be the origin of why the surviving members of that, our current planets, have their axis tilts. They're not strictly from formation, but they're from interactions with other planetesimals as they were surviving. Okay, so basically large random collision like what made the moon gave the Earth its 23.5 degree tilt. At 20, well, we'll leave that alone. So if rotation is the cause of the wobbling motion, then how is rotation making a wobble? I think by what you mean by that is the cause of precession. Okay. And so what causes precession is that the Earth is not a perfect sphere. The Earth has a bulge around the middle. It's an oblate spheroid. So it's got a bulge around the middle. And that bulge then gets a little more extra gravitational pull from both the sun and the moon. And it is that difference in the gravitational pull, those gravities put a force on the bulge, a torque on the bulge. And it's that gravitational force acting on the asymmetry of the Earth that causes the precession. It's just like a top. It's sort of like a top. It's related to a top. If somebody wants to ask that question, what's the difference between a top and the Earth in the discussions, go for it. But the basic answer to your question is what causes precession is that it's gravitational torquing on Earth's bulge. Okay.
And then I'm going to talk a little bit about observational cosmology and a little bit about gravity waves really quickly. So the first question is, I would love to discuss the comparison of observable universe and the age of the universe. Observable universe implies there's more to be observed, but we can only see 13.7 billion years back in time. Is this due to the fact that space is expanding faster than the speed of light? If that's the case, would that imply that space itself is theoretically comprised of tachyon particles? This is a question by JMC Glow 13 in the questions. And okay, so yes, the 13.7 billion years back into time is what sets the limit of the visible universe. I'm going to do a really quick little screen share here. And screen share. And there was actually a really nice plot by Sean Carroll at the AAS meeting. So the AAS is the American Astronomical Society, and I was just at their annual meeting this weekend, and Sean Carroll gave a really nice talk about visible universes and horizon problem and multiverses and whether or not we could use real science to really say anything about these things. And I actually do recommend Googling Sean Carroll and the Arrow of Time to read a whole lot about really fun cosmology stuff. But just sticking to our one universe, we don't actually know what's beyond our so-called horizon. The horizon is the edge of the observable universe, the visible universe, and it's set by the light travel time that it takes light to reach us. So you're always in the middle of your observable universe, not because you're in the innate physical center of the universe, which for all we know doesn't have a physical center. It's just because from your point of view, light travels to you from all directions. And it can only travel for as long as it's existed. And because of the Big Bang, light has not existed for longer than 13.7 billion years. So it's actually 13.7 minus 100,000 years, because that's the point at which the universe stopped being an opaque plasma. But plus or minus 13.7 billion years is how long light has had to travel in our universe to reach us. And so if you try to look beyond that, you won't see anything, because there's nothing to see, because light takes a finite amount of time to travel. This is set by the finite speed of light. The fact that while light is very, 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 very fast, it still takes a certain amount of time to cross space, and space is very, 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 very big. And consequently, you only look so far back. You can only look so far back because the light needs to reach you. So you're basically looking at the edge of the universe, 13.7 billion light years away. What's beyond that horizon? As far as we can tell, based on what we can see of the observable universe, the universe itself is fairly uniform. There's little lumps and bumps here, but the lumps and bumps are fairly uniform. And so we're pretty sure that for quite a ways around us, despite the fact that we can't see it, we're pretty sure that the rest of the universe around us more or less looks like the universe that we can see. We don't know how far out that extends. Does it extend forever? Is there an actual edge? We have no idea. But we can constrain it somewhat from what's called the anisotropy, from the uniformity of the universe that we do see. There's a question about tachyons. Is the rest of the universe expanding faster than the speed of light? Yes and no. Locally, you can never violate the speed of light. It is a hard limit to the best of our ability to measure physics. So locally, at any point inside the universe, you can never go faster than the speed of light. However, yes, from our point of view, this person over here is moving away from us faster than the speed of light, but locally the speed of light is never violated. So that's a good question, and it's kind of a real head scratcher even for me. Then the next question is about gravity waves. And in order to explain gravity waves, I need to do a little bit about relativity. Heaven help me. Special relativity and general relativity are the two theories of relativity. So these pictures here where you see space-time being dented by the presence of the Earth or the Sun, this is general relativity. Special relativity was Einstein's first theory, and it basically just says that whatever speed you're traveling at, you will measure the speed of light to be the same. I just want to say that again because a whole lot of amazing things fall out of that statement. However fast you are moving relative to your surroundings, or however fast your surroundings are moving relative to you, both you and your friend who isn't moving at the same speed, as long as you're both moving at constant velocities, you will both measure the speed of light to be 300,000 kilometers per second. It's really fast. That if you're moving at half the speed of light relative to your friend, so you're coming towards each other and you shine a flashlight at your friend, or your friend shines a flashlight at you, and which one of you measures the speed of light as being 1.5 times faster? Frank, which one of you measures the speed of light to be 1.5 times faster?
Neither.
Neither. You both measure the speed of light to be exactly the same. It doesn't matter if you're looking at a flashlight aimed away from you, forward or backwards. And this is the whole scenario that Einstein sat in a train on his way to his job at, like, what was he working at? Like a stamp factory or something? He was a clerk. Patent clerk. And he would sit in the train thinking about flashlights and moving at half the speed of light, and all of these amazing things, time dilation, space warping, fall out of this. And that's the theory of special relativity. General relativity took him another decade or two. How much later was it?
About there.
Yeah. And that actually is the idea that gravity, mass, the presence of mass changes the shape of space-time. So special relativity creates the idea of space-time, that time is a fourth dimension. We think of space as having 3 dimensions, but when you have this warping of time due to people moving at different velocities, and relativity, it's called relativity because neither one of you was right. Just because you're on the Earth and your friend is moving at half the speed of light doesn't mean that you're right. Your friend and you both have legitimate frames of reference for evaluating the speed of light. So it's relative, it's all relative, and the speed of light is the same. But mass bends space-time, these 4 dimensions of space-time, and this is actually a 2-dimensional drawing of what's actually happening in 3-dimensional space-time. And did I have a picture somewhere? There was a picture here. This is more like what it actually looks like in 3 dimensions. So this is what the 3-dimensional warping of space-time looks like. So what does a gravity wave look like? A gravity wave is when you have 2 things that very profoundly warp space-time, like black holes. And you have 2 black holes which are making these 2 very deep dents in space-time, and they're orbiting around each other. And they actually create a ripple in space-time. And again, in 3 dimensions, it looks more like this. And when they are orbiting around each other because of their tidal forces, they actually will eventually merge into a single black hole. And this creates a very distinctive signal that it was theorized as far back as Einstein that we would be able to detect. Gravity waves are so slight. It's happening so far away, and it's such a slight impact on the Earth's gravity that it took us until now to see it. But here's what it looks like. This is the second detection. The first detection actually was quite a bit stronger because they were bigger black holes. And there was a press release at the American Astronomical Society, though, saying that they'd found another one. I've heard a rumor that they actually have quite a few of these. They're just, sort of releasing them one at a time as they verify their data. So yeah, we've started to see these for real. And then I want to close with this really pretty picture of what the center of the galaxy looks like right now with Mars and Saturn in the center of the galaxy. And if your eyes were bigger and you had really good color vision, this is what you would see instead of just a couple of bright dots. So Frank, I'm done. So I don't know if you want to answer any more questions.
Yeah, I think we've gone past 11. So I think what we'll do is we'll save the remaining questions. We can either answer them in the discussion forum or possibly pick them up for the second Google Hangout. Does that sound okay? Did I lose you? Looks like I lost Jackie. There she is.
I muted myself. Okay, all right, I'm good.
Okay, so I think we'll just answer the remaining questions in the discussion forum or save them for Hangout number 2. So thank you everyone for joining. Just a reminder, you've got homework 3, 4, lab 2, and your first quiz due by next Monday. Okay. If you have any questions on any of that, ask it on our discussion session. Okay, thanks. Bye-bye.